And then today, I'll be talking about the Bayesian optimizations, and then I will emphasize some of the two critical issues. One is a high-dimensional space, and the other one is a combinatorial space in the perspective of the Bayesian optimizations. And then this is a joint work with my previous PhD student and the joint tech teams, and who is currently in the University of Pittsburgh as a postdoc. All right, so if you're not familiar with the Bayesian optimizations, and then this is just the gentle overview of what the black box optimization look like. Okay, so suppose actually we have some of the black box functions f of x, which means actually we do not have any access to the functional form of the f of x. Okay, and then we would like to find the maximizer, hopefully global maximizer of the black box functions f of x. And what we can do here is actually we only are able to evaluate the value of the function f of x at particular query. Okay, and then probably we will get some noise evaluations for the particular queries. So the typically, and the closed form expressions of the function f of x is not available to us. And also the f of x, in general, nonlinear functions or the non-convex functions. And also we do not know the gradient of the f of x either. And also in most of the case, actually, the evaluations requires some huge money and the time, so we are not able to evaluate the function value frequently. Okay, so that is known as actually very expensive noise evaluations at query points. So under this scenario, okay, so we would like to find the global maximizer of the function f of x. Okay, so this is not typical the numerical optimizations. So the typical applications, the well-known application is hyperparameter optimization. So the relation between the hyperparameters of the neural network and then the validation error is not given to us actually. So it's not a closed form of functions. Okay, so we are able to validate the performance of the neural network after we setting up the hyperparameters, and then we train the neural network. Then we are able to evaluate the performance, right? Okay. But that's probably you already know that actually the validations require some the long trainings, and it's laborious and the painfuls. Okay, so we would like to set up we would like to choose the good set of hyperparameters without much training the neural network. Okay, so in this case, this is a typical applications of the Bayesian optimization. So the objective is its generalization loss, and the closed form function is not known to us. And the search space is a hyperparameter settings, and observations is empirical loss of the test set. Okay, and these days actually the Bayesian optimization becomes more popular in the material or the bio areas. So for instance, okay, we would like to design the protein sequence to satisfy the certain goals. Okay, so the sequence design is actually the combinatorial problems. Okay, so the protein sequence is the bunch of the amino acid, and each amino acid consists of the 20 different characters. Okay, so we have to choose some good configurations of the amino acids to satisfy the certain goals, such as like low toxicity or some minimum folding energies, something like that. Okay, so the objective here is the desired performance, and the search space is a proteins or the DNA sequence. So basically it's the strings, and observations is a performance criterion you set up. For instance, like minimum free folding energy. So this is typically the huge combinatorial problems which cannot be solved easily. Okay? So you choose some certain bio sequence, and then they go through the wet experiments to evaluate its performance, okay? So after you're observing the performance and then go back to the sequence design again, and then you repeat this procedure, but it requires some of the huge money and the times. So you like to minimize the number of evaluations until you get some the right configurations actually you'd like to have, right? Okay, so the key things here is actually you would like to minimize the number of evaluations to find before you find the either maximums or the minimum depending on the problems you have, right? So there are a bunch of open source softwares available, and then the first four are rather old, and these days actually the Meta developed a nice the Python the softwares known as a blowtorch. Okay, so the yellow highlight one is the most popular. Okay, because it's developed by the Meta, and the last one is actually the open source software developed by us and by just one of my previous PhD student, known as actually the Bayesian. So there is the GitHub link here. And recently we published our work on the Journal of Open Source Softwares. So if you have interest in this open source, and then maybe you can visit this the site or these papers. All right, so quick overview of the Bayesian optimizations. So suppose actually we have a black box functions, okay? We would like to find the global maximums. So we do not know actually the landscape of the objective functions, right? So the first thing, okay, what we have to do is to figure out the landscape of the objective functions using some few number of the data points we have, okay? So that's nothing but just construct the probabilistic regression models, okay, known as also the sorting models. So suppose we have some few labeled data points, right? And they're using just a few labeled the data points, and then to figure out the landscape of the objective functions using any probabilistic regression method you prefer. But the most popular one is the Gaussian process regressions. Okay, so the Gaussian process regressions tells us that actually what is the posterior mean and then the posterior variance. Then the posterior variance tells us there's some uncertainty of the function values at each point, right? So once you construct the probabilistic models, right? And then you need to choose some nice candidate X, which gives us the maximal values, okay? But the landscape we figure out is not really perfect because we have only just a few number of points, so a lot of uncertainty. So we cannot really say that, okay, so just look at the landscape here, and then this is a maximum, but that's not really true because the posterior mean function has a lot of uncertainty, okay? So what you have to do is actually you build some acquisition functions, which is nothing but just the expected utilities. So acquisition function tells us that, okay, if you choose some particular locations X, okay, and then how much quality of such experiment will have, okay? So there are a bunch of different acquisition functions available depending on the utility functions, okay? And then I will show you some of the exemplary acquisition functions shortly, but once you have a certain the expected utility functions, okay, and then you go through some standard numerical optimizations to find the maximums of the particular acquisition functions to select the best candidate you believe, okay? So you select the one candidate through the AFO, okay? And then you evaluate the function values at the locations you selected through the acquisition function maximizations, okay? Now you have one more data, right? And then you go through the probabilistic regression again, and then maybe the uncertainty will be reduced, because if you have more and more data, and then the less uncertainty you have in the regressions, okay? So you figure out the landscape of the objective functions again with the less uncertainty, and then also construct the Bayesian functions again and find the maximum. But in fact, actually, the theoretical guarantee, which means actually at the end of the day, and then you will be able to find the global maximum, if you find the global maximums of these Bayesian functions, okay? But still, so you'd like to solve some black box optimization problems, and inside you ran into some another numerical optimization problems, but this numerical optimizations is much easier than the original black box optimization problems, but still you should be able to find the global maximums of these Bayesian functions, and otherwise the theoretical guarantee doesn't work, okay? And then I'll get to this point again. And if we apply just some simply just local optimizer to the Bayesian function maximizations. And if you're familiar with the bandit optimizations, okay, and then there are some the close the relations or the similarity between the bandit optimizations and the Bayesian optimizations, although there are some the two different communities. So personally, I started to work on the Bayesian optimizations, and then look at some of the bandit optimization problems later. But a lot of persons, okay, working on the bandit optimizations actually didn't look at the Bayesian optimization carefully. So the two different the communities just developed their own method and the technology actually. But the long time ago when I started working on the Bayesian optimizations, then I thought the Bayesian optimizations is just infinite correlated armed maybe extensions of the bandit optimization, because in most of the case, actually, the bandit optimizations assume just a finite set of chirps, right? So the finite set of actions. Bayesian optimizations assume just infinite number of options. So it's a continuous. So the decision variables are continuous. In Bayesian optimizations, in bandit, multi-armed bandit, actually, the actions are finite. But that's not always true, because even in the bandit problems and the Lifshitz bandit, contextual bandit, and correlated bandit assumes some the continuous options actually. So this is not really the true, but this is a typical the distinctions between the bandit optimizations and Bayesian optimizations. And then I realized that actually the best term identification problems are more close to the Bayesian optimization. So I'm looking into the best time identification problems these days. But in fact, actually, the Bayesian optimizations also referred to as the Gaussian band. Right. So if you remember, actually, the Bayesian optimizations constitute two modules. Okay. So the first module is probabilistic regressions, right? Build the surrogate models to roughly estimate the landscape of the objective functions. And the other module is Bayesian functions, okay? And the probabilistic regressions, and then you can use Gaussian process regressions, or maybe even tree-based, like a random forest models. Still, the random forest can compute empirically the variance of the regression functions. Okay, so I'm not going to tell you about the details on the probabilistic regressions, but on the other hand, the Bayesian functions, maybe if you are not familiar with, and then this is just a brief summary of the Bayesian functions. Okay, so suppose actually we define a utility functions to measure the quality of the experiment. Okay. And then under the surrogate model, we already constructed using the set of data point, we have and then take the expectations to the utility functions under the posterior that we already have in the surrogate models. Okay, so we have a posterior here. Okay, and then this is some of the predefined utility functions, and then nothing but just the expectations with respect to the posterior distributions of the function values. So for instance, okay, so these are the typical acquisition functions people frequently use. And the probability of improvement is nothing but just to assume that utility is nothing but, this is an indicator. So if so we select some particular location X, and the Y is a corresponding function, noisy function values. So function value or the evaluations at particular location X is greater than the constant alpha, and then the utility is 1 and otherwise 0. So this is an indicator function. So the argument is true, then the value is 1 and otherwise is a 0. And the most popular acquisition functions, which is expected improvement, is nothing but just the utility function is this indicator, and then the gap between our function values and then the threshold alpha. Okay, so this is nothing but just the value. And also the GP versions of the upper confidence bound is the sum of the posterior mean and then the scale posterior standard deviations. Okay. So for instance, the GPUCD, so we construct the Gaussian process regressions for the surrogate model, and then we have to choose some of the candidate. Okay, so the sampling rule depends on, okay, so we would like to select the point X whose posterior mean is large, and also the posterior variance is also large. So in other words, the posterior mean is large. That means actually we have a high chance such X to be a maximum, right? If the regression is very correct. And then the posterior variance is high. That means actually we have a very high uncertainty at a location X. That means we might have a chance that location X, we might have the maximums. Okay. So in fact, actually, this acquisition functions trade-off between the exploitations represented by the posterior mean and explorations represented by the posterior variance. Okay. So for instance, this is an example of finding the global minimum, right? And then initially we have 4 points, which are denoted by the brown color cross. So here, here, and here, and here. Okay. So that's the initial set of the data, right? And then we do the Gaussian process regressions, right? So the blue color is our posterior mean constructed by the GP regressions. Okay, so using the 4 data points and then do the GP regressions, and then we gather the posterior mean represented by the blue solid color, and also this shaded reason is confidence intervals, maybe the 95% confidence interval. Right? And then we construct the GP upper confidence bound here, okay? And the maximum is located around here, okay? So this is the yellow cross is the locations where the acquisition function is maximized, okay? So this is our next candidate we would like to choose, right? So we selected this one, and then do the function evaluations, okay? Because although we do not have any functional forms of the f of x, but given some particular quantity x, we are able to find the value f of x or up to the noisy versions, okay? So now we have one more the labeled data, right? Okay, and then we do the GPU regression again, right? So the posterior mean is changing, but still it's the blue color is a new posterior mean, and the variance will be changed, okay? And then construct the acquisition function again, the GPU CB, and then find the maximum, which is here. So we selected these ones, right? And then we do the GP regression again. Okay, so once we have the accumulate more the data points, okay, and then the uncertainty will be reduced, right? So if you do the GP regression again, and then the last uncertainty around the support of the X, right? And then construct the acquisition functions, and then select the maximizer of the acquisition functions, which is here, okay? And just to repeat these procedures again and again. And then after a few the rounds, and then we are able to find the global minimums. So in fact, actually, this is very simple, the procedure, and then the applications may be getting larger and larger, okay? So in a lot of different communities, and then they realize, okay, so the usefulness of the Bayesian optimization, so they just try to employ the Bayesian optimization idea to solve their own problems, okay? So recently I started to work with the AI assistive, the drug discovery company, right? And then they also have interest in the applying the Bayesian optimizations to reduce the time and the monies in finding the new the drug discovery. Okay. All right. So how do you measure the performance of these the algorithms? And then the performance is measured by the regret. Okay. So instantaneous regret, which is known as actually the suboptimality gap, is just nothing but just between the X star is actually the global maximizer, but of course we don't know, right? And so the global maximum, and then X sub t is our choice, right? So what is the gap between the f of x star and the f of x t? Okay, so this gap is large, okay, and then our choice is not good, right? So the gap should be as small as possible. Then our choice is getting close to the global maximizer. Okay. The cumulative regret is just the sum of the instantaneous regret up to the number of rounds of the large t. Okay. And then the simple regret is nothing but just the gap between the optimal and then our best choice. Okay, so we tried maybe the 10 different rounds, okay, and then the best choice will be the maximum of f of x t, okay, so that the gap, okay, should be small. So if we design an algorithms, and then we would like to design an algorithm that the accumulations of the regret grows sublinearly, okay? So in other words, if we just increase the number of rounds, okay, and then the cumulative regret divided by the number of rounds, maybe should approach zeros, right? Which means actually we just keep trying, and then at the end of the day, and then we will be able to find the global maximum, okay? So if this is, okay, so the sublinear growings of the cumulative regret is actually the no regret algorithm. So in the Bayesian optimization literatures, okay, and always they present some algorithm, then they prove the algorithm is actually the no regrets algorithms. Okay. Okay, so the GPU-CB was already proved, and this is really nice papers, and the regret is actually grows a sublinear fashion. Okay, so I'm not going to go into all the details, but in fact, actually, this was published in the year 2010, and then I believe that actually this paper was awarded maybe in ICML the Test of Time Award. So in other words, in the year 2020, and then this was the most impactful work the past 10 years, I guess. Okay. So back to the acquisition function optimizations, and I told you that actually to prove the no regret algorithms, and then we should find the global maximums of the acquisition functions. Okay, so global optimizers such as like direct or evolutionary search are able to find the global maximums. Okay, but it takes time. Okay. So in practice, and a lot of people just simply use the local optimizer like some well-known numerical optimization technique like LBFGS, right? So in practice, it still works pretty good, okay? But I was interested, okay, so what if the performance degradations occurs if we use LBFGS instead of the global optimizers, okay? So it turns out that the gap or the difference between the instantaneous regret occurred by choosing the local optimizer, like LBFGS, okay, and also so this RTL is the instantaneous regret determined by the using the local optimizer, and RTG is the instantaneous regret determined by the global optimizer, but the gap between these is not really big. So the gap between these two instantaneous regret, the probability falls inside the some epsilons, okay, has some very high probability, okay. But of course, depends on a couple of things, but this is not really the critical things, okay. But in practice, when you run into the numerical optimizations, okay, sometimes actually you use the multiple start, okay. So you select some initial conditions and then run your local optimizer, and then choose some of the different initial conditions and then run another your local optimizer. So if you just run your local optimizer using the multi-start, and then you will be able to get a better solutions, okay? So if you choose some more multi-started local optimizer, and the gap is getting smaller and smaller. So in fact, actually we proved, and then this the graph shows us that actually if you just run the multi-started local optimizer, and then the performance is getting close to the case where you use the global optimizers, okay? All right, so let's get to the high-dimensional the Bayesian optimization problems. So do you have any questions so far? So far, actually, just a brief overview of the Bayesian optimizations, but I'm not sure actually are you guys familiar with these techniques, or maybe you're in some, okay, maybe some of you might be familiar and some of you might not, okay. So in the Bayesian optimizations, so you have the decision variable x, right? So the x is the vector. So if the dimensions of the x is greater than roughly 15, and then we consider that's a high dimensional problems, okay? So if it's greater than the 15s, and then the complexity is getting larger and larger, okay? So standard Bayesian optimization assume that actually you have a continuous decision variable whose dimension is less than 10 to 15 dimensions, okay? So that's the typical assumptions. But what if we have some maybe 100 or 1,000 dimensions of the decision variables? and then you are not able to apply some standard techniques. So, okay, there are a couple of other problems. Okay, so of course, search space grows exponentially with the dimensionality, right? So it's a huge space. In that case, actually, the global GP model may not fit the data everywhere, right? Because you have a very small number of the data points, okay? But if you use the global GP, and then doesn't work. And also a lot of areas have some diffuse uncertainty. So for high-dimensional problems, and typically this leads to the over explorations. So to solve these problems, and a couple of approaches have been developed. And then the first idea is actually, I mean, the low-dimensional embeddings has been around in many different places, right? Okay, so instead of working in the high-dimensional space, okay, so you move into the low-dimensional space, assuming that there is some low-dimensional subspace, okay? And then working in the low-dimensional space, and then back to the original space, okay? And also, there are some additive decomposition techniques available for the GP, okay? So you have some many number of input variables, okay? And then you use additive models. So, and each of the modules will be described by the GP. And these days, actually, the more interesting idea is the local Bayesian optimizations. So instead of a search, your global maximums or the minimum over entire search space, but instead actually you restrict your search space to some of the local regions, okay? Which is described by the trust regions, okay? So you do the local search or the local optimizations, and then if you do success and you enlarge your trust region, if you do not, and then your trust region gets smaller, okay? So that's the one idea. The Turbo used the trust region techniques for the local search for the Bayesian optimizations. And the other, the technique utilized actually the gradients. So in the beginnings, so this is the idea of the trust regions. And then instead of searching over entire space, and then you construct some of the trust regions where you can find where you believe actually your solutions live with very high probability, okay? So you construct the trust region, and then just to do the local search in the trust regions. And then the trust region, the size will be enlarged or get smaller and smaller depending on you make success in finding the better solutions or you fail, okay? And the other, the technique is known as actually use simply, okay, so if you do the local optimizations, and why not using the gradient-based techniques? But in the beginning, I told you that actually there is no information about the gradient of the objective function, how we can use the gradient informations. It is well known that actually right? Okay, so using the set of data points you have, and then you construct the surrogate models, which is roughly estimate the landscape of the objective functions, okay? So that is described by the Gaussian process. And also you can differentiate of the objective functions, and the differentiation is a linear operator, right? So the linear operator of the GP is also the GP, okay? So you construct the joint GP over the objective functions, and then its derivative, okay? So using the set of data points you have, and then you estimate the gradient informations, okay? And using that informations, and then you do the gradient ascent or the descent, okay? So that's also the popular local things, okay? All right, so that's some idea of the high-dimensional problems, and then now gets to the actual the main the topics of our today's talk on the combinatorial problems. Okay? So the standard Bayesian optimization assumed the input vector x and elements of x are real values. Okay, so it's a continuous and bounded between some two numbers. Okay, but what if we have the our decision variables x is simply the binary numbers, for instance, and also you can easily convert your categorical variables into the binary numbers. Okay, so for the sake of simplicity, I assume that actually the x belongs to the Boolean space. Okay, so it's a d-dimensional space, but each entry is either 0 or 1. Okay, so suppose actually you have the d number of choice, and that each options you take it or not. So that's a typical combinatorial problems. So just like a standard Bayesian optimizations, and you'd like to find the global maximums of the black box function f of x, but only difference is x lives in the Boolean space. Okay, so it's a small change. But the techniques will be much different. So there are a couple of problems, right? So the GPL regressions relies on the columns, which measure the similarity between the two points, right? Okay. Or maybe if you are able to measure the distance between the 2 points, and then that's okay. So the similarity and the distance, okay, will carry the same information. Okay. However, suppose that actually you have a smallly Boolean vectors. In such a case, there is no natural orderings over some bunch of Boolean numbers, right? So we cannot really. It's not easy to measure. Okay, so which one is close or which one is not. Okay, so we need to construct some right kernel functions to measure the right similarity between the two Boolean vectors. Okay, so that's the one, the critical issues we have to take care of. So in general, categorical variable that doesn't carry the natural ordering, so there is not easy to directly construct the right kernels. Okay, and also even in the Bayesian function optimizations, actually, it's combinatorial domains. Okay, so it's really difficult to combinatorial problems even for finding some optimums of the Bayesian functions. Okay, so two major challenge. Okay. So of course, maybe there are a number of different approaches to solve this combinatorial Bayesian optimization problems. And then the first one is actually, okay, so the pseudo-Boolean function means actually the input is Boolean, but the f of x is the real values. Okay, so that's actually the pseudo-Boolean functions. So it is well known that actually there is some free expansions of the pseudo-Boolean functions. And then some particular technique assume that actually the free expansions of the pseudo-Boolean functions up to the second order. Okay, but of course, maybe third order, fourth order, but they just cut off up to the second order to make it simple. So once you have the free expansions of the f of x up to the second order, and then this is okay, and then you simply just apply the Bayesian linear regressions to figure out all those parameters. So that's replaced the Gaussian process regressions in the surrogate to construct the surrogate models. Okay. And also, in order to use the diffusion kernels on the graph, okay, some idea construct the combinatorial graph, okay, in the case of the combinatorial categorical variables, and then they build the combinatorial graph, and then they can construct the diffusion kernels. So that is well known. And then my interest is also the embedding techniques, okay. So my work is based on the embedding idea that I would like to share with you today. So the technique known as actually the CBO randoms. And in fact, actually, this was published or presented in the Uncertainty in AI 2 years ago. And also the similar idea was also developed. I believe actually the other one is better than my old ones, okay? But probably how it explains my own work in today's. All right, so okay, so this I skipped this idea, okay, and then go to the my own work. Okay. All right, so probably you heard that actually. So low dimensional embedding, and then suppose that actually we are in the categorical space, okay? Categorical space. So we need to solve some optimization problems in this categorical space. Okay? But you transform your problems into some another space through the certain transformation fee, but this embedding space is a continuous. Okay, then you can easily apply your standard Bayesian optimizations in the continuous space. Okay? So you do the standard Bayesian optimization in this continuous space and back to the original categorical space to solve your original problems, okay? Just to keep doing this. So this is known as actually the latest space Bayesian optimization, I guess. Okay. So from categorical space to the continuous space, so this embedding is done by maybe encoder, right? And getting back will be the decoder, right? So the encoder-decoder structure is right, I mean, very popular in the deep learnings, right? So one way to do this is actually you get access to the unlabeled data, right? So the bunch of X only, right? And then maybe you can train your favorite autoencoder things like variation autoencoders or some other the pre-training techniques, okay, to figure out some find some encoder and the decoder. So once you find the encoder and decoder, and then you can easily embed your data into the different dimensions or the different space, right? Okay. So, but that's not my ideas. So what we did is actually, instead of using some encoder and decoder trained using the bunch of unlabeled data, but instead actually we would like to do the random projections, okay? So maybe we don't have to train the encoder and the decoder. So, but what if we using the random projections, okay? So the starting point is, okay, so we have, I mean, our problem is on the Boolean space or the categorical space. So the X is the categorical variables, right? But if you embed your data into the continuous space by the random projections, and then the embedding space is a continuous, and hopefully some maybe the low dimensions, okay? So that we can easily apply the Bayesian, standard Bayesian optimizations. But these random projections preserve some things. So, but there is the well-known theory, and then under certain conditions, and the random projections approximately preserve the distance between the arbitrary the data points. So in other words, this is known as actually the epsilon isometry embedding. So we embed set of n points in d-dimensional space, n points into some lower dimensional space, all to the k, while maintaining the Euclidean distance between the original d-dimensional space. So this is actually what we would like to do. So this is original our the d-dimensional space, and then the distance measured by the delta. So okay, so the distance between the x of I and x of j is a delta. And then you do the random projections, okay, and then embed your data into the k-dimensional space, and the distance between the y sub I and the y sub j is maybe up to the 1 plus epsilon delta, okay? So this is known as actually epsilon. So if we can construct this random projections, preserving the distance up to the epsilon contaminations, okay, and then our goal is satisfied. Okay. So our curiosity is, okay, so there exists such the random projections, okay, or the linear map, okay, and if exist, okay, how we construct such a linear mappings, okay. So the Johnson, Linden, Strauss lemma tells us that actually there exists such a linear map which guarantees some epsilon isometry embeddings, okay, and the construction can be done by the random projections, but of course maybe not arbitrary random matrix. There are a well-known family of the random matrix which is satisfied this distance preserving guarantee. And then what is the minimum target dimension, which means actually what value of the k we have to select to preserve the distance up to the epsilon tolerance, okay? And in fact, actually the minimum target dimensions depends on the number of data points in the original space, not the dimension d, okay? So if we have a more number of data points, and then target dimension will become larger and larger. Because intuitively that's true, because you have a huge number of data points, and then you have to preserve all the distance between all possible combinations, okay? And then maybe the target dimension should be large, okay? So if you have a smaller number of data points to preserve the distance, okay, and then maybe the target dimension is small, okay? So the JLMR, okay, has been widely used for the random projections. That means, okay, so the square root distance between the f of x of I and f of x of j is bounded by the 1 plus minus epsilon, and then the distance between the x of I and x of j, okay? All right, so this is well known, but in our case, the combinatorial problems, okay, and then distance in the original space is not a Euclidean. It's maybe we have to take the Hamming distance, for instance, right? Because we have only just the Boolean vectors, right? So the Euclidean distance is not a good measures, right? So the Hamming distance between the Boolean vectors is nothing but just L1 norm between the difference, right? So the Johnson-Linden-Strauss lemma also holds even for some of the different norms, especially the Hamming distance. Yes, fortunately. So in other words, okay, the Z is a categorical vectors or the Boolean vectors, and the phi is embedding, okay? So in embedding space, the square Euclidean distance is bounded by the 1 plus minus epsilon and the Hamming distance. So this is exactly actually what we want. So, but in fact, actually, this can be easily proved following some of the previous work, okay? But this is actually the main theoretical things actually, which allows us to develop our own method. Okay, so in our original, the Boolean space and the distance is measured by the Hamming distance, right? but such a distance is preserved by the random projections in by the Euclidean space in the continuous space. Okay. All right. So in this way, what we can do is, okay, so we do the random projections, okay, to embed our the data points to the embedding space, and then just run our standard Bayesian optimizations in the continuous space. But we have to figure out, okay, so suppose that actually in embedding space, and then we discovered one candidate Z. But in order to evaluate the function values, and then we have to transfer our candidate Z back to our original space so that we can evaluate, okay? So in our case, actually, when I do the random projections, and then we also just we assume that actually the random projection is an injective function, so that there is some one-to-one correspondence, and that we keep the values between the X and the Z, okay? So that we can always returning back to the original space using that relations, okay? So we keep some of the tables, but that's what we can easily do, right? And also, we were able to prove that actually, even in our case, the regret is still the sublinear. So that, but the bound, of course, compared with the original, the GPUCB, the bound is a little bit getting bigger because we do the epsilon isometry embedding, okay? But still, we are managing to the sublinear, the growth of the cumulative regret, so that we are able to find the global maximums of our original problems, even in the combinatorial space. So that's the main message. So for instance, let me just show you a couple of experiments. It's a synthetic experiment before I conclude my talk today, because the time is getting close to the 3 o'clock. Okay, so the first experiment is actually the binary quadratic programming. Okay, so this is a binary quadratic programming problems. Okay, and then the Q is D by D matrix, and X is the binary vectors. Okay, and then we would like to find the maybe minimum of these quadratic functions. And then we do the combinatorial Bayesian optimizations to find the minimums of this the binary quadratic functions. Okay, and then this is the result. Actually, so the X is actually the 10 dimensions. In fact, okay. So the y-axis is actually the regret, and the x-axis is a number of rounds to proceed. And compared to the bunch of other techniques, and then the best result is achieved by this the random projection technique that I introduced today. Okay. And also in Ising model specification problems, it means, okay, so we have some Ising models which meet some the distributions, the Gibbs distributions, and then the variables are simply just the binary, either -1 or the +1s, okay? And then the matrix J is interaction matrix. Okay. And the distributions over yes, this is not really Y, but this should be V. Okay, so the distribution is there is some the distributions, right? But we would like to find some approximating distributions well match the true distributions. Okay, so the Q is our approximate distributions. Okay, and then we have to figure out, okay, and then the true distribution P, and then this is our approximating distributions, and then to minimize the KL divergence, and then the support of the V will be the graph. Okay, so the X is tells us that actually the indicator variables, so there is a connections between the nodes or not. Okay, and then apply the combinatorial Bayesian optimizations and the once again and compared with some other techniques, and then also this nicely work. And also when you do the subset selections in the sparse regressions and the classification problems, so in the subset selections, which is maybe the familiar to you, and then you have the many different choices of the input variables to achieve the best performance. So for instance, like in the sparse regressions, and you would like to choose the smaller number of the input variables still maintains the good performance. Okay, so there are many different configurations, and the best configurations can be obtained by applying the combinatorial Bayesian optimizations to the sparse regression problems. Okay, so that's also one thing actually you can do even for the classifications. And then recently, we applied our techniques also combined with the trust reason. So when you work in the high dimensional problems and still you embed your data into the continuous space, but still the embedding space is also not really low dimensions. Okay, so instead of doing the global search, and then you can combine with the idea of the trust reasons with the random projections. And it turns out that actually the blue curve is the regrets over the iterations. Our original, the random projection-based combinatorial Bayesian optimizations. And then the green and also the orange curve is the result of our technique combined with the trust reason. And it turns out that actually much faster actually to find the solutions. And also some other application or some other problems still be observed that actually the combined with the trust reasons, it helps a lot. Okay? So that's something actually we are working on. But I think actually I better stop here because I already explained my own work, and then maybe I can take a couple of questions from the audience, or if I have questions from the online, and then maybe I can answer it. Okay, so thanks a lot. Yeah. Okay, sure.
I have two questions. So first one is I think first part of your presentation, we use Gaussian process to find a theoretic function. Let's say this function is our loss function, and the variable is our hyperparameter.
Right.
So after you build this theoretic function, so after that, how to find the maximal global maximum?
Oh, okay. Okay. So maybe for instance, the question is okay. So for the hyperparameter optimization problems, and the result of the Gaussian process tells us that actually what will be the generalization error if I select such configuration of the hyperparameter. So that's not actually the training error. Okay, so the training error function is well determined by the, say, maybe scared loss or the cross entropy loss, but the generalization loss induced by the hyperparameters, we do not know the landscape actually. So it's not the model loss. Okay, so what we can do is, okay, so typically we select some set of hyperparameters by us, and then trained our neural network, and then using the validation data set to see what is the generalization error look like. And if you're not satisfied your validation error, and back to the setting of the hyperparameters, and then you just select some of the different configuration of the hyperparameter, just depending on your experience. And then training the neural network again, and to then also evaluate the generalizations. So you have to go through this procedure. So what Bayesian optimization help us that actually instead of choosing the hyperparameter by your experience, the Bayesian optimization tells us that, okay, what will be the next best choice of your hyperparameters, which expected to give us some better generalization method. Okay. So that's actually through the acquisition function optimizations tells us that the best next candidate of the hyperparameters. Okay. So we use the hyperparameter configurations recommended by the Bayesian optimizations, and then train our neural network, and then evaluate our generalizations. So evaluations of the generalization error will correspond to the function evaluations in this setting f of x. Okay. So then we have one more data point. So one particular configuration of the hyperparameters, and then the label will be the generalization error. So we have one more label, the data point, so that will construct the better landscape of the objective functions using the GP regressions. Okay.
Question about more practical. So you mentioned the training neural network or recently large model is very expensive.
Right.
And if we parallel new hyperparameters, we get trained model and the validation error. It's difficult. How about, do you think it's possible, like we don't need to train the model till the end, but we
only stoppings,
yeah,
like only stoppings, or just using the chip trainings?
Yeah. Can we use such parallel result?
That's a good question. Okay, so maybe the full training is really painful, right? Because it takes really time. So instead of the full trainings, and what about just using the only stoppings, right? So it saves the times. Okay, but if you just repeat just only stopping, and then maybe I don't expect some good performance, but this might be possible. Maybe once in a while, you do the full trainings, but frequently just to do the early stopping, and then it's the few number of cheap evaluations, and then one full evaluation, and combine it together, and then you get the better idea. And then that is known as actually also that's possible in the Bayesian optimization framework. Okay. And then there are some work using that idea. Yeah. And also this is also possible. You have some good resource. Okay. So you can train the neural network using some of the different number of choice of the hyperparameters. So parallelly, you can train the neural network. Maybe say you can train your 10 different neural network at the same time. And then instead of just searching sequentially, you can select the batch of the candidate at the same time. So maybe every time you select maybe the 10 candidate and evaluate the 10 candidate parallel fashions, that's also possible. Yeah. So if you have plenty of the resource, and then yes.
There's one question online.
Okay. There were just the potential user of techniques, and then maybe we can discuss later if you have so many more things you would like to discuss.
If I can ask the final last question.
Mm-hmm.
How, if you have an experience, how data hungry are those methods? Basically, I have some collaborators that have like large and different data sets, but they have very low number of samples. And they ask me, don't do any data like reduction, like
So this works is starting from the initially very small number of the data set. Like it depends on the problems, and it depends on the dimensionality of the input X. Okay, but it's the dimension is really huge, and the initial is really small. Then maybe the performance is not that great. Okay, but this idea is okay. So although you have the small, very small number of examples, right? Then, but using the small number of examples, and then you roughly estimate the landscape of the objective functions, and then you just find the one candidate, and then do evaluations, then maybe your data is increased by 1. So you start from the maybe 5 data points, and then one round, okay, you will give us the one more data. So then maybe the 6, and then do again 7, maybe. But as long as actually you can evaluate the candidate through some experiment, okay, and then still maybe will be okay. Yeah.
Okay, thank you very much. No more questions. So once again, thank you for this wonderful talk.
All right. Thank you very much.